today. Welcome to the Inventing Talk. We're happy to have here Marc Stevens. Marc Stevens is well known for all his work on breaking hash functions, in particular undefined SHA-1. And today he will talk about breaking SHA-1.
Okay, thank you. Thank you very much. I also want to thank the program committee for inviting me to give this talk here. And indeed, I will give my this talk on breaking SHA-1, which has been widely expected by the entire community. I mean, we've been working on it for, I think, almost 2 decades, at least already on it. So this talk will not just be about the final attack where we succeeded, but also will be about the research that went into to get there and the obstacles that we had to cross. And basically, for the start of this work, a lot of the techniques to attack SHA-1 were already invented, and it's really about going the last mile, and this last mile really took a long time. So I've been working on this since 2009, so that's also about 10 years already. And of course, this work that I've done this presentation is based on joint work with Angel Team, Eli Gerstein, Pierre Karpman, Jarek Barkov, and Thomas Perrin. So the structure of this talk, I'll of course give an introduction and talk about basic techniques for SHA-1 collision attacks that we've developed in the first decade. Then there was really some sort of a bottom, like where there were no really advances anymore, and there was clear there were some particular big hurdles that have to be crossed to really get towards a practical SHA-1 collision attack, which I will then address, like which steps did we take to really address these hurdles and optimize the SHA-1 collision attack. So of course SHA-1, as we all know, is a cryptographic hash function that maps arbitrary length bit strings to a 160-bit bit string, which was designed by the NSA in 1995 as a fix of SHA-1. And basically, unless you're an IOTA developer, a cryptographic hash function should be collision resistant, which means that it should be hard to find different X and Y that map to the same output. And of course, the best generic attack costs 2 to the power 80 SHA-1 computations based on the birthing parameter. However, it's now very clear that SHA-1 is not collision resistant, because there is a known collision attack for SHA-1 that has complexity 1, which we found with the 2 to the power 63 SHA-1 cost computation that we announced. So this is how this complexity 1 SHA-1 collision attack looks like. It has a fixed same prefix and 2 different messages, and it just outputs this message block. And of course, it can produce an infinite number then by simply appending some random bit strings. And well, we spent a very large computation to actually find these bit strings. But in general, for any hash function, these type of algorithms really exist. So that's also why they exist, but they are not known. So which is why collision resistance for hash functions is defined informally. We don't really have a formal definition. So SHA-1 is of course based on the Merkle-Damgard paradigm. Basically, there's the hash function takes arbitrary size inputs, but then it uses a compression function with fixed size inputs, namely 160-bit chaining value and a 512 message block, and will output 160-bit chaining value. And then simply any message will be padded and broken up into message blocks of 512 bits, and then starting from an initial value, it will just simply repeat the compression function and will output the last chaining value as the hash. And of course, Merkle-Damgard is known for the security reduction. If there's a SHA-1 collision, you actually have a collision for the compression function, which means that if F is collision resistant for this informal notion, then also SHA-1 is collision resistant. And the compression function from SHA-1 is actually a block cipher in Davies-Meyer mode, right? So it's a block cipher where instead of a key, the message block is input as the key. And basically the input chaining value is the plain text, and the output chaining value is simply the cipher text sorted or added with the input chaining value, the Davies-Meyer feed-forward. Now this compression function has an internal key expansion, which is in this case of course a message expansion, which is linear. So The first 16 words are simply parsed from the message block. 512 bits are parsed as 16 32-bit words in big endian, and then the remaining words are basically expanded with a linear regression function. Then the compression function itself is a 5-branch Feistel block cipher with 80 rounds. So this basically describes the Feistel update. We have 5 state words of 32 bits. There's a Boolean function. We have bitwise rotations. We add a message word, and we add a known constant there. And then everything is rotated. Now the very nice thing is that we can actually describe this whole state update actually just as a linear function, or as a non-linear function, but it's completely described in the AI. So we can get rid of this whole rolling state. So towards the collision attack, well, essentially the goal is to find a collision for different inputs. And of course we're going to apply differential cryptanalysis, so we're going to fix good message differences, delta m, and then we're going to try many inputs, pairs of inputs m and m plus this difference until we find a collision. And actually, of course, we're going to apply this to the compression function itself inside, so we're going to find a collision of this form for a certain chaining value. We're going to have a pair with a certain difference in the message block with the same output. So this looks like this picture. And the nice thing is, of course, that we're in a hash function where instead of a random or unknown key, we actually have a message block as the input as the key. And we can use this our control of the message block to amortize cost of this search. And actually, the first 16 steps are very easy, right? We have complete freedom over the message block to just practically fulfill any conditions. And then the next steps are very tricky, where we can use some smart modifications, and we can still amortize costs of finding solutions up to a certain step. But then, very clearly, the remaining steps are hard, right? And they are probabilistic. So it's very important that we find good differences where this probability is very high in order to get a low complexity or feasible complexity. And the main problem if you just attack a single compression function is that, of course, we require that here these output differences in the output ciphertext of this block cipher are 0. And this severely limits our possible choices for the message block differences, in so much that we haven't been able to find any feasible attack faster than brute force. So the solution, because of the Davis-Meyer feed-forward, is actually to use 2 blocks. Right? So the first block will have some output difference d, and then with the second block we can actually cancel this because of the Davis-Meyer feed-forward. We only have to flip the sign of this part and basically get an opposite sign difference in the output in the second block. And in particular, we're going to use the same high probability differential over this part, but then we'll have 2 different input differences. Here it's a 0, here is this delta d. And so that means we really need some tailored nonlinear differential path to basically connect this input chain value difference to this linear differential. And basically this approach allows just any arbitrary difference delta d, and indeed it's possible now then to find a feasible collision attack. And Wang et al, they were able to show that this really works, and they presented the first theoretical attack with a cost of 2^69. So the basic techniques the SHA-1 collision attacks rely on is, although first the main part of the complexity is this differential L. So this really has to be high probability, and Chabon and Zhu showed in '98, 20 years ago, that you can do this by using local collisions, where you have a local collision is just about 6 steps of the 80 steps of SHA-1, where the first step will insert some bit difference in the state, and the remaining 5 steps, they will cancel this difference. And then basically you can have a disturbance vector who puts all these local collisions together. Basically this disturbance vector is just a representation of all the state bits, and every 1 bit in this disturbance vector marks a bit perturbation, so the start of such a local collision. And a nice property that really enables the attack is that if this disturbance vector satisfies the message expansion, this linear message recursion for the key expansion, then actually the final differences that we're going to use in the DAC also satisfy the message expansion. Right? And this is really currently the only known way how we can achieve this restriction and obtain high probability differential health. So then we still needed to find these dense differential paths, and there are various algorithms. Actually, of course, the first nonlinear differentials were actually found completely by hand, which is very hard to reproduce. But there, after that, two types of algorithms were found. One by de Gagnère and Rechberger, based on the guess and determine approach. You will utilize generalized conditions over bit pairs. And we start with no conditions at all, complete freedom, and then we repeatedly add a restriction and then propagate this information to find other restrictions that are then necessary. And just repeat it until you have found the full differential path, and of course you have to backtrack on a possible contradiction. And the other approach is the middle-to-mid approach, was originally presented by Yajimi et al., later refined by myself, where basically you construct this nonlinear path. You start from the chaining value, you start from the linear differential, you work towards each other, and then in the remaining 5 steps in the middle, you just perform an exhaustive search. So that's basically how to construct this, the idea is to construct a linear differential and a nonlinear differential, and now really to speed up the attack, to even further amortize the costs. Of course, in the first 16 steps, it's very easy because we have complete freedom. So the more interesting techniques for the remaining sort of 8 steps, but this can really be a longer number of steps if you do a lot more effort, are the following steps. And they basically all do the same, right? So they take a message pair that basically satisfy a differential path up to some step, and they're going to modify it and will give you another message pair that hopefully will satisfy also conditions up to the same step or even more. So Wang et al., they introduced message modification where they changed message bits, and with really the goal that they correct unsatisfied state conditions. They were really looking to basically, if there was a state condition unfulfilled, that they would then put in a correction. Whereas other techniques, they really just try to amortize costs, right? If you have a solution up to a certain step, just generate more solutions up to that step so that the amortized cost of finding a solution up to that step becomes cheaper. And then neutral bits is very simple. It's a single message bit freedom that you just defer until it really affects the conditions of your differential path. And then there's boomerang, which is much more complicated. It's essentially an auxiliary differential path, so it's much more complicated differences that you would apply modifying one message pair into another one. And this is definitely the stronger technique. So in 2005, the first theoretical collision attack was found, and of course we immediately saw a lot of progress by practical attacks breaking reduced round SHA-1. So the first years were very productive, and we quickly got to 70 rounds. Then sometime later, 73 rounds were broken, and then in 2011, finally 75 rounds were broken. And this already, they used this GPUs because of the high complexity. But regarding the collision attack on full SHA-1, the picture is a lot more complicated, right? We have the original attack, theoretical attack, presented in Crypto 2005, and after that there were definitely a number of claimed attacks on full SHA-1 given in talks. So one gave a talk at NIST, Sugita et al. They had a 2 to the power 5 modification, so it's still unclear what the real complexity this is, published at FSE 2007. Of course, Mendel et al. Gave a talk about, a run session talk about their Boeing search that they launched, which would have a collision attack complexity of 2 to the power 60.x. But eventually this Boeing search was abandoned in 2009. And finally, there's a PhD thesis by Raphael Chet, which claims a complexity of 2 to the power 58. But one of the problems is that all these claims, they don't have any public source code, so it's very hard to verify the accuracy or the complexity of the claims, right? So in particular, it's very unclear what this complexity means, and we don't even know the differentials, or a lot of details are actually missing. So after some time, it still became clear that sort of 2 to the power 69 was still the benchmark. And it also became clear that we're definitely finding a SHA-1 collision in practice was a lot bigger challenge than expected, right? So the progress from the leading teams stalled. An actual running Boeing project it was everybody had its hopes on, was abandoned. And so sort of the main hurdles that I've heard from people is, also adding myself some hurdles to it, is one is the practical cost is still too high, which is also why there was a Boeing search, but even there, the actual progress it was very slow. So just the practical cost 2 to the power 61 or 60.x was still a bit too large for an academic effort. There were problems with too few degrees of freedom, which of course you can, because there were basically undefined equations, which of course you can solve by just using many nonlinear paths, basically gaining your freedom there. But this of course creates issues because you have to re-optimize for, potentially re-optimize for any new nonlinear differential path. And what I've also heard from other teams is that the complexity estimates different theory of practice, right? So they have an estimated attack complexity, and when they actually implement it, they actually see some other results. So they really appear to be hidden costs or phenomena behind, which might also be related that systems are really dense and over time. And finally, it is mainly a hurdle for myself, is no public source code, not of the attacks, but also of the attack tools. So basically, when you really want to start this researching on this, basically have to develop all tools again. So it will require quite a bit of an investment. Right? So bottom line, actually in 2009, it was not really a recommended research topic for anyone to start at that point. Right? It was already shown very difficult. The leading team's progress has stalled. You have to put in a large investment, and basically, you sort of know in advance that your odds of success would not be very great. So, how I got into SHA-1 cryptanalysis? Well, I did my master and postgraduate project on only 5 collisions, which were quite successful. And actually, in late 2007, I started my PhD on algebraic geometric codes, so completely different. Having already done some hyperelliptic curve work with Tanja Lange. But then in 2008, we were contacted by some hackers, and they noticed that some certification authority was still using MD5, and I basically was allowed to switch my PhD topic to improve MD5 collision attacks and attempt to construct this rogue certification authority, which turned out to be very successful. And basically because of this success, I really had the freedom to just not go back to algebraic geometric codes, but really to pursue, to dive into this SHA-1 challenge. But of course, I didn't take this very lightly. So the goal is to find a collision before 2012. At that time, I thought it might be realistic, and of course, after that, it just turned into next year. But I definitely had a plan on what I wanted, how I wanted to improve the current state, right? How to get more optimal attacks, how to get over these hurdles. And the main part, which I really spent most time on, is improved linear differential analysis, right? Really get a higher accuracy in these linear differentials and basically obtain higher success probabilities and thus a lower complexity. Right, so this approach was applying meet in the middle strategy to the nonlinear path was actually quite easy. I read my entire MD5 work was based on meet in the middle. It was actually quite simple to move this to SHA-1, and this offered the benefit of more degrees of freedom. That was already quite clear early on. So that, and then finally, the idea, I've already been working with the GPU implementations. I mean, it was very clear that they're more cost efficient. So these were sort of my ideas how I could address these hurdles. But this one was sort of already done. But then these were the main research problems, right? How can we get an improved L differential analysis where we really get a higher accuracy and basically are able to really optimize the SHA-1 collision attack? And optimization for the SHA-1 collision attack is really important. Of course, we need accuracy, that you really get the results in practice that you expect from theory, but optimization is very important, right? Any factor 2, given this large cost, can mean the difference between a 1-year computation or half-a-year computation. In the end, we sort of also got up by better hardware. In the end, it only took 8 days, so the factor 2 is now only a difference between 8 or 16 days, but that's only the matter of a large number of GPUs that Google volunteered for us. And the fact that these architectures improved over all these years. So optimizing the attack, so that's really, we've already seen that most of the techniques to attack SHA-1, they were already invented up to this point. So really it's now researching how we can really bring it into practice and really optimize the attack, get higher accuracy, get a better results, matching results between theory and practice. And the most important part is the L differential, right? So the collision attack complexity really crucially depends on the probability of this L differential. And this L differential is just essentially a block cipher related key differential, right? The nonlinear differential will give you some state difference delta I, and this is going to be probabilistic. So we're also going to input these message word differences, and we're just interested in a probability that we'll get the target difference delta O on the outside. So this is what we really want. And then basically the problem is how can we accurately compute the probability of such a differential? And then the next important question is how can we determine the maximum possible differential? And of course, what is it? So up to that point, there were basically 2 used practical approximations. One is without carries, where you basically use a single optimal differential path. And in cryptanalysis, we have various tools that allow us to compute optimal differential paths or differential characteristics based on branch and bound, but also linear programming and SAT and SMT tools. They will, are tools that in principle can give you optimal differential paths. And that will give you an exact probability. The problem is, at least for SHA-1, is that this is really a first order lower bound. And it's been very clear, it was already shown, that really carries give a significant improvement. So there's another way to approximate this probability of a linear differential, is basically taking these local collisions and then assume their independence. Because the local collision is only 6-step, and it's very easy to compute the probability for that local collision. And then we can just combine these probabilities. And indeed you get higher probabilities. Only here the problem is that you get approximation errors because these local collisions are not in fact completely independent. Right? So they might have the same condition, and then you either get contradiction or you can get higher success probability. So basically, these problems, even though they're very practical approximations, they really help you to build an attack, they don't really allow you to determine the optimal differential or even the optimal conditions for your differential, right? Really the minimum set of conditions so that you can attain your differential. So when I started research, my first attempt was to get a more accurate probability. It was basically to just simulate what really happens in a collision attack, but a little bit more smartly, right? So I was going to use a stepwise Monte Carlo sampling process. I was just going to sample states with differences as they would occur in a real collision attack. And I'm going to assume that differential paths that don't follow the disturbance vector, right? The disturbance vectors specifically specify where differences should be, and of course we can allow carries. But other than those differences, I don't allow any other differences. And then there's this very essentially simple Monte Carlo approximation, right? So if you start with an input set of sampled states for step I, you can just go to the next set of sampled states by just randomly sampling from here n times, take a random sample for the message word pair, and just extend with step I, and then check whether this matches the disturbance differences, and then if yes, then you add it. So basically, in a stepwise process, we can sample state pairs for a certain step that match the distribution as in a real collision attack, and at the same time, we sort of get the probability associated, the real probability associated with that particular step. And then we simply have to basically multiply all these probabilities for these individual steps, and that would be the approximation for the L differential. And indeed, if you have very large n, you really get small approximation errors. And eventually these will become negligible when n goes to infinity. But in practice, these are small on average. And it basically means that this probability is still not accurate for all delta W. So not for all analyzed differentials. And of course, there's this problem that you have that there's still very large complexity, right? So we need every step basically takes n iterations, and we need a very large number of iterations to get small approximation errors, and we basically have to repeat it for many delta W differences or for many differentials to really try to find the optimal one. And so that's why I used a GPU implementation, but even in practice, it still had limits. But this really already gave a lot of progress because it really allowed to determine near optimal differentials that really closely match what I got with the later tools that allow to give us optimal differentials. And another problem with this approach is that I do get a close approximation of probability. I don't get conditions associated with this, this differential. And that in particular means it's difficult to glue to a nonlinear path. But the success of this approach really got me thinking, and I really got some inspiration in trying how to improve this. And sort of to get there, suppose this sort of trivial approach where we simply analyze all differential paths that match the disturbance vector. And then if we let Pi be the set of all partial paths up to the I step, then we basically can easily compute Pi plus 1 from Pi by extending the paths from here and putting it in the set. And from this last P80, we can actually easily compute all L differentials from it by just grouping together paths that have the same L differential properties. And this approach basically immediately trivially gives you optimal differentials and also optimal conditions because we can simply select. We have all the information that we would want. And of course, this trivial approach doesn't work in practice, right? Because with every step, the number of differential paths will grow exponentially. So this will quickly will not work. But with a Monte Carlo sampling, we sort of also had something very closely approximating the real distribution. And my thinking was that maybe we can follow this approach, but we don't have to keep all the information of the differential paths, right? So the idea is to use Ri that represent these Pi, but really in a reduced form, and in a strongly reduced form, where basically the set Ri mostly has size related to the number of active local collisions at the beginning and the end, and not related anymore to local collisions in the middle. But then, of course, we need this representation, and we need two key algorithms, right? We need to be able to extend Ri into Ri+1, and when we reach R80, basically there should be an extraction algorithm that allows you to indeed extract all L differentials from R80. And then sort of the research question became like, which representation can we use, and which is the optimal one, or like what's the minimal representation that we can use, that where we will have where this approach will be successful. So basically, my first attempt was Monte Carlo, and my second attempt was basically this approach, where I used a differential path representation that was just based on a set of differences for the state bits and the Boolean function output bits. And given that representation, we can also just define a reduction algorithm where we eliminate differences that are not strictly needed anymore when we want to extend the differential path. So assume we have this sort of reduction, then these Ri store basically tuples of reduced differential paths and some probability that's associated with all the possibilities that would, in the middle of the differential path, that would complete the differential path into a real differential path. And then we take this path, we extend it into a set of extension paths, which are basically follow the same representation, and then we just reduce it. So we eliminate differences from this extended path, and we also get the probability of these differences that we've eliminated. And then we just store this correlation, the reduced differential paths, together with the the probability of recently reduced differences and the probability of all accumulated differences. And we add it to this. And basically, this is a bit of a simplified representation, but for instance, in my thesis I show that this is completely mathematical correct. That this works. In the end, you will get optimal L differentials. So how does this reduction looks like? Well, we have this representation of a path as a set of state differences and Boolean function output differences. So for every active Boolean function bit that has some input difference, we sort of group this bit to all the three input state bits. And so so we get a bunch of groups related to the active bits, Boolean function bits, and then we're going to merge these groups that have overlapping state bits, right? So where they basically use the same state bit for their outcome. And when we do this iteratively, then the final groups that we get are really disjoint, and it also means that they're actually statistically independent. And that's very nice, because then we can safely remove these groups that are not related to the input and the output difference. We can just remove them from the differential paths. They're not really necessary anymore when we want to extend them, because they're essentially statistically independent from the input and output. So when we have differences, we group them, and you see the blue ones, they correlate with the output difference. They're statistically dependent on the output difference. And these gray marks, they're disjoint, and they're actually statistically independent from these output bits, and we can just remove them. So this is sort of the visual representation of the reduction process. And the good news is that this actually works in practice for good disturbance vectors, where there are still relatively few local collisions, but still at that very large time and memory complexity. So for a bit more complicated disturbance vectors, which have a bit more local collisions, time and memory really became an issue. So that's why I actually went into a third solution in the end, where of course we're going to group the active Boolean function output bits to the input state bits, but now we're only going to merge groups that have overlapping bits and where they really have a statistical dependence on these overlapping bits. And now the final groups are not necessarily disjoint anymore, but they are still statistically independent, which is still sufficient to show correctness, to really correctly obtain all L differentials at the end. And then again, we're just going to remove all the groups disjoint, and we also output this reduced path and this probability. This really is a bit more complicated because the statistical dependence check is really dependent on a particular Boolean function. So you really have to try almost sort of do an exhaustive test over all these overlapping bits and really to check whether there's a statistical dependence or not. But this really gave a significant improvement in time and memory complexity. So it really made it a lot more practical to compute the L differentials for local disturbance rates, also in more and more precision. So this work on computing optimal L differentials covers a number of publications, but in the end, we really are able to practically compute all L differentials for disturbance vectors, where basically we compute L differentials over all differential paths that match the disturbance vector. And then once we have this, it's very easy to select the optimal L differential that has the highest success probability that we really want for to minimize the attack complexity. But it also allows us to choose the optimal conditions. We can really choose the minimal set of conditions where we can attain the success probability, and that basically also gives us additional freedoms for the attack. And the nice thing is that this approach is very, very flexible, so we can extend this approach where we not just have an input difference, but actually there's an input differential path, so a fixed differential path in the beginning steps, where we basically really want precise conditions so that it becomes easy to optimize the attack cost, also in combinations with these managed modification techniques. And it also means that it now becomes very easy to glue with a nonlinear path, right? So if we optimize for this, then we can give this different input differential path. We can give this to the nonlinear differential path construction algorithm, and automatically they're correctly glued together. And we really know what to expect for the conditions and success probability. And another nice feature is, of course, that we actually, for the final steps, it has already been known that you do not necessarily want to follow the disturbance vector, so you can also, with a bit more work, you can also let go of this approach, where you just allow arbitrary differences. And this indeed can give a higher probability. So in particular for our disturbance vector choice, we really get a factor of 2 by just using differences that don't follow on the disturbance vector. But this is very rare. Basically, I've only seen this for 3 disturbance vectors where you get a higher probability with non-DV-based output differences compared to just DV-based output differences. And this approach is not only flexible, it has also various applications. Well, of course, we want to select optimal L differentials, right? We really want to minimize the collision attack complexity towards this SHA-1 collision attack. But it's also possible to use it for other purposes, right? So in particular, if we're able to select a very large set of very good output differences that all have high probability, they don't have to have the maximum success probability as that we want for the just normal collision attack complexity. Then, but if we just want a large set of good output differences, then this allows us to minimize the chosen prefix collision complexity, because the size of this set basically depends on how many blocks we need, and also determines the birthday search complexity that we have to use before we. So that there is a birthday phase where we don't want an internal collision, but we want an internal. We want a certain target difference after the birthday search, such that the remaining attacks on the compression function can eliminate this difference. So with a larger set, we can have a larger set of allowed differences for the birthday search, and thus the birthday search will have a lower complexity. And then, if we all have all the L differentials, we can actually start to prove properties of these L differentials. And this was important in a related work on SHA-1 collision detection, where basically we are able to prove necessary conditions on these message word differences. And these message word differences, these necessary conditions, they are very easy to check. Right? To check for a collision attack, you had to do a complete compression function call, but to check for just a simple message word condition, you rarely get the message at first hand. So this is just a 2-bit linear equation that's very easy to check. And this really significantly allowed to improve SHA-1 collision detection, basically from a factor of 32 to just a factor of 2 times just normal SHA-1. And this really made a difference why it is now actually inside Gmail, Google and Microsoft Drive, and actually also now in Git and GitHub, really protecting against SHA-1 attacks. Not just our single SHA-1 collision attack, but basically any collision attack that is based on a list of 32 disturbance vectors, which were chosen to be the best 32 disturbance vectors. And even though this does not repair the full collision resistance of SHA-1, basically this list does allow us to sort of claim a repaired collision resistance of SHA-1, I think up to complexity about 2 to the power 70. So then the remaining part of the attack, the L differentials, was really a significant portion where I spent a lot of time on. But then the final steps, we also have the nonlinear path construction, and this was already developed for MD5, and it was easily ported to SHA-1. So just a meet-in-the-middle approach on very few steps. And essentially we're going to do exhaustive search over 5 remaining steps in the middle, but the nice thing is that we actually can do this with a sort of a bit scanning approach, which is very, very efficient. But the benefit from this meet-in-the-middle attack is, meet-in-the-middle approach, is that only on those 5 steps we have very dense conditions, and then actually for the remaining steps, everything is very sparse. Right, so for instance, if we compare our second block differential path, which is a bit more dense than the first block, and this, I believe this was the first block for the 70 round collision, where you can sort of see, I mean, this isn't inherently limiting the guessing determinant, but at least the meet-in-the-middle tool really more efficiently gives you to really pack all these conditions very early on, giving you a lot of where the remaining parts is really sparse. Of course, for the second block in particular, this was so dense that actually with all the additional conditions, this became over-defined and was unsolvable. And of course, we can try many variations, but our tool was not really did not easily allow this. So for the final collision attack, we actually used an SAT tool to just basically find the variation of this differential path that was in the end solvable with all the additional conditions we get from the rest of the attack. But this is very nice, right? So now we are able to put all the conditions basically completely up in the front, and also together with the SA2 tool, we are really able to handle any IV and basically able to connect it to the L differential efficiently. And then finally, even with optimizing the linear differential and the nonlinear differential path, we still have a very large attack cost, and so to really make it a more practical academic effort, we really want to switch to the GPU architecture, right? Because the GPU architecture really has a lot of cores, right? Current CPUs, well, nowadays they can go up to 20 cores or a bit more, but GPUs really have a lot more cores, like 1600 for this GTX 970, on which we did a lot of development. But then this is also a limited platform, right? So there you have warps, which are 32 threads that really operate in lockstep, right? So there is a single instruction, multiple threads. And if different threads in this warp want to do a different instruction, then these are serialized. So any divergence or any branching between these 32 threads will become serialized, and it means all the other threads become idle. So there's definitely a big pitfall that you really have to do some work, prevent branching, to really make efficient use of the platform. So the problem is our SHA-1 collision search is a depth-first tree search, which is of course completely, at least for a CPU implementation, completely consists of for loops and a lot of branching. So just a straightforward depth-first tree search is not suitable for the GPU. But basically we remodeled our software, the collision attack search for the GPU, where basically we want a single warp of 32 threads to just process the same single step, right? That they would do the same work. And to do the depth-first tree search, well, they sort of have to pull work. They also always have to look at the last queue, right? We have partial solutions that we're going to extend in each of these steps, and these are in shared buffers, where all these warps will input and output to. And then so every warp just chooses the last step to really get the depth-first tree search, and to make sure these shared buffers don't overflow. And then basically with this approach, the only divergence of these threads within warp is basically whether or not they were going to write a result, right? Whether or not their output is valid, satisfies the conditions of the attack. So this GPU framework, although it was very clear from the beginning that GPUs have a very significant benefit, it's still not very trivial to implement. And so we chose to basically develop this GPU framework in a number of iterations, where we really started looking on freestart collisions for SHA-1, basically because just produced round collisions for SHA-1, they were ready so far, and it was hard to improve on that, so we started looking on freestart collisions. And then our first implementation, for just 76 round SHA-1, we only implemented neutral bits, so just keep it simple. And this was very efficient. Only took about 5 GPU days. And then with a further refinement of the GPU framework, we also implemented boomerangs, and this really allowed us to do a freestart collision attack for the full SHA-1. And since it's also completed the GPU framework, we could now give accurate estimates for the cost of a full SHA-1. And you can really see the benefit of going towards the GPU architecture, right? So the collision search, one GPU does the same amount of work as 140 cores, and that was for the GTX 970. Since then, GPUs have progressed. There are even new versions out there, also with more cores, so you can get even more out of one GPU. And if we compare this to raw SHA-1 on one GPU, you see that raw SHA-1 still has a much higher performance than for the collision search. So for raw SHA-1, one GPU can do the same amount of work as 320 cores. So it does mean that moving from the CPU architecture to the GPU architecture, we do lose a factor of 2.3 because we have to cope with this different architecture. But still, nevertheless, right? So this factor really means that a GPU attack is much more cost efficient than a CPU attack. So looking at the real-world attack costs that when we finally ran the attack, it was very nice that Google volunteered the infrastructure. They really wanted to work with us to really run the attack, and it was not simple, right? They volunteered their infrastructure, but we had a double-blind access to it, right? We didn't know exactly what they were running on it, how they were running on it, and so we had to give source code. They had to modify the source code for their infrastructure. But it was double blind because for them they didn't understand the source code, right? And this was actually a problem, right? Because there were several issues, not just in the job management. For the GPU code, we used features of the CUDA framework that were allowed in our own private server, but weren't allowed in the infrastructure. And this wasn't allowed, but it was also a silent failure. So in particular, like automatic memory transfers, when you switch context between CPU and GPU, their compiler said, okay, yeah, this is fine, but then when they actually ran it, want to run it, they apparently didn't work. But trying to figure out what went wrong in this kind of situation where we don't have access to immediate results and they don't understand the source code is really difficult. So the first near collision attack actually used the CPU implementation of my Eurocrypt 2013 paper. The source code was already public at that time, basically because we didn't want to invest in GPU. So we could already prepare for the second near collision attack while the first near collision attack was already running. And this took about 2 to the power 60 SHA-1 compressions, and we actually that covers the cost for 2 attacks. So we actually had a little bit of choice for the second near collision attack. And this cost weeks on like 100,000 PCs. I don't have clear numbers from Google. But this was definitely a choice. Since the source code was available, just immediately start running this. Whereas the second near collision attack, that's really the more costly, right? You can see that this is the more costly effect, part of the whole attack, and we implemented this on GPU. Of course, we faced hurdles, in particular, like these over-defined nonlinear paths that were unsolvable in practice that we had to fix with SAT. So it took a bit longer to build the attack, but in the end, we managed to build the attack. We managed to get a working implementation on the Google side, and they basically ran this on 5,000 GPUs all over the world inside Google. So they also used GPUs from AlphaGo, where they got complaints from, what I've heard. And in the end, that's now the very nice thing, it only took 8 days. So when I started this research project, I was thinking I really have to optimize for a factor 2. I really have to optimize everything, because this factor 2 can make the difference between practical and not. And in the end, not just, also because of the large infrastructure, and because of the GPUs and all the optimization work that went in there, in a way we sort of overshoot, right? In the end, it only cost 8 days. Maybe we could have, in hindsight, spent less work on some things, because maybe 30 days was also fine. So, some conclusions, lessons learned. I mean, clearly this project was more difficult than expected. I mean, it was already clear because of the work up to 2009. But for myself, I started in 2009. I targeted in 2012 for my PhD. But in the end, only finished in 2017. But that was still definitely in time, because in February 2017 we found a collision. But then that was also the month of my tenure track decision. So I got tenure in March 2017. So with respect to that was completely on time. But it also shows it took 8 years. So there was really slow progress with a lot of hurdles. And this is not just from an academic point interesting, what are these difficulties. From a personal side, this is also very hard, right? So if you target in 2012 and every time it just takes another year and you get one more hurdle, of course it's very clear that this project was very important. The community was looking forward to the final result, everybody was expecting it, and it should be done. But it doesn't mean that it makes it personally easy when you ran into all kinds of hurdles and never really knowing whether you actually will be able to finish it. So that's also my my lesson learned, to really stay realistic about big challenges, right? So understand when you go into a long-term investment, and this typically should not be for PhDs and postdocs, because they have to publish or perish, right? They really need publications. And with such a big challenge, with really a lot of large body of work, it becomes hard to publish in. And you also have quite low odds of success. So there's high risk, but definitely for SHA-1 there was also high gain, which is a big part of the motivation for me. I also found this is really that public source code is really important, right? So from 2009, we still really couldn't compare these claimed collision attacks because we didn't have source code really understanding what the claim complexities are and how to collect them. So we need them for viability of claims, but also to understand what are now these differences between theory and practice to really try to find these hidden phenomena. But I think it's also important to support further research, right? So if there's a lot of work done and somebody wants to start on the same topic, but he has to redo everything, and in particular for SHA-1, there was a lot of different tools that needed to be built, right? So that really takes a lot of investment. So if we would all publish more source code, we could also have really increased the productivity of our community. So in particular, I want to, of course, point to my relevant GitHub repositories related to this work, where you can find a lot of tools for this work. And then finally, I also have some open questions, which I would really find interesting, and also want to look in the coming years. So what are the impact of dedicated attacks in quantum? Right, of course we have world research, and also we have some nice results, cryptanalytic results really going into modes. But for these type of really dedicated cryptanalytic attacks, how can we move these kind of ideas really into the quantum world and make effective use of them? For instance, there is also a quantum research algorithm which also gives a quadratic speed up. It isn't easily applicable, so that's definitely how can we apply this? Because the quantum treesearch basically expects the same kind of freedoms at every step, which clearly you don't have with the SHA-1 collision attack. So how could this be modified? This? And then actually, I mean, I spend most of the time on this research on algorithms for optimal differentials, and I think it's a very nice question. It's like, is this more applicable to other block ciphers or other symmetric primitives? Right? Of course, for SHA-1, I mean, it's really on this disclaimer. I only analyzed differential paths that follow the disturbance vector, which was really critical, right? So for SHA-1, this was possible due to this local collision structure. But this isn't necessarily inherent to this idea of reduced form, right? So what are other possible enabling structures to do this kind of work? And that's sort of my final slide. So I would like to thank you for listening to me, and yeah, thank you.
Are there some questions for Marc? Yeah, I have a question. So for MD5, you did these certificates, these client certificates. Can this also be done for SHA-1?
Well, I mean, clearly the colliding certificate cannot be done in practice anymore because the whole CA browser forum, they moved away from SHA-1. Oh, can I get back to my slides? But I think this is really important. Our final attack was 8 days. It was the majority of the computation. Right? And with this L differential tool, I think it might be possible, I hope, that maybe a factor 16 might be attainable, or at least a relatively small factor that it could still be practical on 5,000 GPUs. Yeah.
Okay. Okay, dan thank Marc again.